Recording is on.
Okay, hi everyone. Hi Karunya. So last week we discussed some of the graphs topics, right? So we'll continue
Okay.
on the couple of problems on the graphs. Okay. So let's look at deeply. So we discussed about BFS, how to do the BFS, and we discussed about DFS, right? And we also discussed about kind of finding a circle in DFS, right? So do you remember last time, like
Yes, yes,
BFS
yes,
is like
correct.
going one level at a time. Can
If
you
it
hear
has
me?
two, yeah, I can hear you. If it has two paths
Yeah,
for the
yeah. Go
same
ahead. Yeah.
destination, we ended up as a circle.
Exactly, exactly. Yeah. So something like this, right? So if you have like this directed graph, so you can think of as a circle, right? If you start here, you can or yeah. So this is one of the circle, right? So we need to that is one other thing. So we found that whether there is a circle or not using BFS. So basically BFS will go like a level by level kind of thing, like trees, right? You will cover all the nodes, and then you will cover all the nodes on the next level, and then it will cover next nodes. So BFS will go down all the way to the down when you visit all the way, right? If there is no path, let's say if this is not there, right? So it will go all the way here. Let's say A, B, C, D, and E. So it will go A, B, C, D, and then come back, and then it will print E. So it will go all the way to the end of the uh, node where you cannot have any more paths, right? So in terms of BFS, A and then BE, right, and then CD. So that's how it is. So we discussed about those last time. Now, here is the problem that we want to discuss today. Given a directed graph, find if we have a path between two nodes using BFS. Okay, so
Okay.
given a directed graph, so directed graph means like we have this. Let's take an example here. I already have an example. Yeah, so here is one example 5, 7, 8. Okay, let me draw it 5, 6, 7, 8. So 6 is a little bit here. I want to draw something here. 6 is here. So now 6 has another route, another path. 9 here. Okay. 6 connected to 9 and both connected to 10. So let's say this is a directed graph. Okay. So directed graph means all the directions, right? So we'll have directions. Okay.
Okay.
So now, given two nodes, we need to find whether there is a path. Let's say we have 8 and 10. Do we have path between 8 and 10? True,
Yes,
false.
there is a path.
Path. True. So now let's say 7 and 6. Do we have 7 and 6?
No,
Do we
there
have
is
a path from 7 to 6?
no.
False. Because it's all directed, right? You can start here, 7. There is no way you can go to the 5 because it's only one directed, right?
Yes.
So how can we do this? So this is the problem. So let's say you we know both BFS, we know both BFS and we know DFS. So
Okay.
BFS will go. Let's say you want to start with 8, right? Yeah, BFS, you will go all the nodes of all the successors of 8, which is only 9 at this point, right?
Yes.
So and then from 9 you will go all the way to the what are the next nodes, 10. So when you're going, you can count whether you whether the node which you are visiting is the node you want. So let's say from 8 you go to the 9 and see, is this the 9 is the destination node? This is the destination, right? So our
Yes.
destination is 10. So this is not the destination. And then from 9 you will go all the directions and see whether if you find any of the destination,
Okay.
right? So it's just similar to the same problem we had. So we need to see how can we achieve this. So another thing here we want to note down is, um, we don't want to visit the same nodes again and again. That will also possible, right? Let's say we have something like, so let's take an example. Yeah, it's a simple example here, just an example, 9 connected to 5, like this. There's a possibility, right?
Oh, that
So
is a cycle then.
you start with 8, right?
Ah,
It's a cycle. That's okay. There is nothing mentioned that there is no cycles, right? Here they said, given a directed graph, find if you have a path between two nodes. So there is nothing said there is no cycles. There could be cycles.
okay.
There could be cycles, right? So here the problem here is, if you start with 8, right? Let's say, this is using BFS. Let's take the BFS route. Let's take the BFS route. Okay, you
Yes.
start with 8 and you go to all the nodes, existing nodes of 8, which is 9, and 9 is not the one we want. And then you start with 9, go visit all the nodes of 9. Okay, okay. So now
Okay.
all the nodes of 9 is 5 and 10. 5 and
Okay.
10. Okay. So now let's say, just an example, this 10 is somewhere down the line, somewhere here. Just an example. This is not the 10. So now what will happen is, let's say this is a 15, something like that. So now 9 has two nodes, 5 and 15. Okay. Still there is a
Yes.
path here, but now you will explore 5, and what are the 5, uh, what are the elements of the 5, what are the adjacent nodes of the 5? 6, 7, 8, right? So again 8 will come up. It's kind of circle. See that again, when you are taking from, you will process 6, you will process 7, when you process 8, again it will come to this step. So basically we will search again and again. It will end up into an infinite loop,
Hmm.
right? So we don't want to the nodes, we don't want to visit the nodes which we already visited, correct?
Yes.
This is exactly the same. Last time we did the same thing. We used a hash set, right, to understand whether we visited the nodes or not.
Hmm.
So similarly, we have to use the same thing. There's a way, right? So either, yeah, because what happens is, like, from 9 you can go to the 5, and again from 5 you can go to 8, and you keep on searching this circle forever,
Hmm.
right? So
Yes.
you know, sometimes, like, you never be able to reach 10 in situation. So that is where what we need to avoid. So that's the main point here. So how can we find a path between two nodes? So using BFS algorithm. Okay.
Okay.
So another thing here is trying to find here. Sometimes you may not be able to find the shortest path. This BFS is. I'm trying to find an example. Let's say, here is. I'm trying to find an example. Here is another graph. Okay, so EDF. Okay, EDF and CB and AG. Okay, so find a path between A and F. How many paths we have between A and F?
And we have two parts. We have. Oh, sorry,
Two
three
paths,
parts we
right?
have.
So I think this,
Three.
yeah.
A, C, and
So
F. Ah,
three, yeah, all the way from A, C.
B and F. A,
We have
C, D,
multiple
and F.
paths. A,
Oh,
A, C, B.
yeah.
Yeah, A, C, B, and F. A, C, D, F, and A, G, F.
And F. Ah,
Right? Basically,
yes.
G connected with F here.
Yeah.
So 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 AGF is the shortest, right? Answer is, the shortest path is basically just AGF.
Yes.
That that is shortest, and another path is ACBF, is
Yes.
longer. Even though you can
Longer.
go to, let's say this is a directed graph, right? Yeah. So ACBF, you can also go this way, but it is longer. So longer in the sense number of nodes. Here, we don't know the distance. Like if it is let's say from G to F is like 100 miles, but ACBF is kind of shortest path. Even like if you go AGF, right? AGF is 150 miles, but if you go with ACBF just 100 miles, then this is shortest. But this is unweighted graph. There are two differences, right? Unweighted means there is no weight, there is no value for the edge. So weighted graph
Yes.
means every edge has a
Which will
value.
have value.
What is so 6 has a 6 to 9. Exactly. Every edge has a value like 50 kilometers, or what is the price? Either it could be price or it could be distance. There are different types of weights. Okay. There could
Yes.
be both. Let's say these are these different stations or different airport stations, airports. Then there is difference, right? Like if it is trains, we'll have kilometers, and we also have a ticketing. What is the value? What is the ticket value from this to this? So sometimes the edge can have multiple weights,
Values.
multiple values. Okay, but here, yeah, here there is no value. Here there is equal value. Unweighted means there is no value. Basically, A to G and G to F is equal time. Similarly, A to C. So you can think of as every node has the same value. Then what happens is AGF becomes, so you want to go AGF, right? So it's like only one. So let's say two. Weight is two here. Just imagine, just only you're touching only two edges, right? If you go with ACBF, right? ACBF. So just three, right? One, two, three, three edges. So in this case, definitely this is the shortest path, right?
Okay.
Are you following? So that
Yes.
is
Yes.
that is the intention. So sometimes it yeah. So in order to find this, we need to write a little bit of extra code to find it. So how many edges you are touching. But in the normal case where this is the first algorithm where you don't care. So this particular algorithm which I'm going to show you here, this will not give you the shortest path. Sometimes it will give you longest path. Okay. So
Okay.
it may give you ACBF. So that's okay. But in order to find the shortest path, you need to have additional logic we have to write. So this is the additional logic I will show you. Basically, we will see how much depth you are going, right? So let's look at the normal algorithm first, and then we look at the other one. So first one, as I said, we want to use the BFS, right? When you
Yes.
want to use BFS, definitely we have to use the Q. Just this is a kind of very kind of hard. We have to hard code in our minds, right? BFS means Q. BFS means stack,
Yes.
right?
Yes. Yes.
Yeah.
So,
So there are two ways actually. Yeah. Go ahead. Any questions? Yeah.
no, 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 Suresh. Yeah, proceed.
Yeah. So basically, the algorithm is like this. So graph is here, and we need to find, do we have a path exist. It is not giving a this particular algorithm. This method is to find the path, but this does not give you the shortest path. Okay, to reach from start node to end node. This is the one we need to check. Basically, this will tell you only boolean. Do we have a path or not?
Okay.
Okay, so this won't give you what is the path. This won't give you what are, well, give me the stations, or give me the nodes which you're going to visit. This algorithm won't give that. Okay,
Okay.
so this will tell you whether a path exists or not, based on the arrows. Basically, if you say path exists between 7 and 6, false, because there is no arrow from 7 to 5 or 5. So you cannot go anything out from 7, right?
Okay.
So that's what it will give you. It will give you only true and false. So this could be one of the smallest interview questions. They won't go deep. Hey, tell me the shortest path, or print the shortest path. They may not ask you that deep. So this is the simplest question. They will ask you, hey, this is the graph, tell me whether there is a path between 6 and 7. True, false. Very simple. We don't need to think deep about the weights or path, right?
Okay.
So the answer is, so the answer the our main intention is start with the start node. Let's say this is start node, right? Start with
Yes.
the start node, and navigate. Navigate whatever algorithm you want to use, BFS or DFS, and see whether you can find the destination node.
Mm.
At some point, you don't go anywhere. You cannot go anywhere. Then you can simply stop. Let's say from 8 to 6. Let's say another algorithm like 8 to 6. Can you go to 8 to 6? First we
No.
will start with 8. So 8 will go to 9, and then
9.
9 is not what we want. From 9 to, let's say, 10. 10.
10.
So you will go to 10. 10 is not what we want. From 10
9.
there is no other paths, right? Let's say
Yes.
there is nothing here. So then we'll stop here. So
Okay.
you don't visit any of the nodes in the graph. This is not normal traversal. Last time we started with traversal where you visit every node. Here we don't need to visit every node, correct?
Yes.
We visit only the nodes from the starting point, which is 8, to the until you find a dead end. Basically this is a dead end. You cannot go anywhere from 10, even though there are other nodes 6, 7, 8. So finally you stop here and say, okay, we are done. There is no path between 8 and 6.
Hmm.
Okay.
Okay.
So as I said, let's say this particular loop is, so if you start with 8, it will come to 9, and the 9 will show you a path to 5. 5 will show a path to 8. So I think I was wrong. So if we don't have this, if we don't have this, then there is no path. But if you have this one, right? If you have this one, there is a path from 8 to 6. Correct?
Yes.
What is the path from 8 to 6?
Now 8 to 6, 8, 9, 5, and 6.
Exactly. So if we don't have this, then there is okay. So if we don't have this, right, then there is no path, right?
Mm.
So um, we want to avoid the circles. We want to avoid the what we call the loops. Let's say loop is like this. Let's assume that loop is like this, just from 10 to 9.
8,
So
9,
so
10,
you
11,
start with 8, you go to 9, and 9 will
10.
tell 10, and 10 says 10 adjacent node is 8, so it will go again. So we don't want to visit the nodes which we already visited, correct?
Yes.
Right.
Yes,
So
yes.
let's assume that 10 has another nodes. 10 has other nodes. We have to visit this. Definitely we have to visit this. There could be 6 here, there could be 6 here, we don't know. But we don't want to visit 8. So there are two ways. Either we have to use hash table or hash set, right? And the
Yes.
other way is, if you are constructing the node. Another way is, if you are constructing the nodes, basically if you have the control or the node. Basically if you are constructing node object, you can have a status. You can have a
Okay.
status on this particular node, whether it's
For
visited or
each
visiting,
node, we
or not
create a
visited. You can have.
status. Okay.
Exactly. For each node, we no need to maintain a separate hash table, right? If you have that status, when you're initializing the nodes, everything is unvisited. Every node is unvisited because you haven't started your algorithm. When you started your algorithm, okay, I started this path from 8 to 6. Okay, so I will mark 8 as visiting, and from 8 to 9 and 9 to 10, like whenever you touches another node, you call visiting another node, visiting. So
Okay.
once you complete Okay, you visited 8. Once you complete visiting 8, you change it to visited.
Okay.
Visited. So that means it's completed. It's completely
Yes.
visited. Now 9 is visiting. So now let's take the 9 and take all the adjacent nodes of 9 and put it in the queue, because BFS use the queue, right?
Yes.
And you can mark everything as visiting.
Yes.
So visiting, and this is completed. Now this completed visited. So now whenever you're starting from 10, right? What are all the adjacent nodes of 10? There are four,
Adjacent nodes.
there are
No.
four adjacent nodes of 10. 8.
And then the three
Adjacent nodes
node.
means the next nodes, right?
Yeah,
The
I
the
know. I
the
know. I know.
connectivity node,
After eight,
adjacent
there
node,
is three nodes. Yeah.
right? So yeah, after 8 has only one adjacent node, 9, right? 9
Yes.
has only one adjacent node, which is
Which
10.
is 10.
Now
And
10
10
has
has
four adjacent nodes. Yeah,
including 8.
10 has four adjacent nodes, right?
Yes.
This is one node, 8 is one node, and these are the three nodes. We don't know what is the values. Now
Okay.
10 has four adjacent nodes, but we don't want, because this node is visited. This node is
Mm.
visited. We don't want to add that into the queue, because there is no
Okay.
point. You already visited that node. You already explored all of their adjacent nodes. So that's the way to do it. So you just add only these three nodes, because these are the only ones which are not marked as visited or visiting anything.
Yes.
Okay. So
Okay.
this is another way of doing it. So rather than using a hash set, rather than you can also put in hash set, right? Basically, before you putting into the queue, you will check whether this particular node is in the hash set. If the particular node is in the hash set, that means it's already processed. Don't do it. Otherwise, do it. It's another way of doing it. You can use the hash set, or you can mark the each node with a different state.
Okay.
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 So
So what
that's
we
the
are going
algorithm I want to
to,
show you.
what is
So
the
is it
algorithm we are going to implement, Suresh? Are we going to implement hash set or
I
state?
will show you both.
Okay.
I will show you both. Yeah, I did both of them. So the main objective is we need to return just true or false. The whole thing,
Okay.
either you can use hash set, you can use this status. Only thing is there are three inputs. One is the graph, and the second one is the starting node, and third one is the destination node, source and destination. And the return value is boolean, right?
Okay.
So here is the here is an example. Here is an example graph here, and here is the enum I'm talking about. So we can use this for if the graph node already exist without this node state field. So basically we will visit only the nodes. Okay,
Okay.
so we can use this. So this is the enum. So you know enums, right? In Java or somewhere,
Enumeration.
enum.
Enumeration.
Enumeration, yeah, enumeration, that's right. Exactly, means enumeration. So we use the three things: visited, unvisited, visited, and visiting. Okay.
Okay.
So here is the node data, and this is very easy, right? So next node means the adjacent nodes, and this is the node data yeah, constructor, and this one is the node, the variable, and this is the method, and here is the thing, node state.
Yes.
Basically this is the state,
Okay.
right? So the state I'm using, this state as a node state. So
Okay.
this is the enum. Okay.
Okay.
Now graph is simple. Graph is very simple. Graph is simply a list of nodes, that's it. It could be
Okay.
connected or unconnected. It could be 1,000 nodes or we. So all the connections will be inside the graph node. So right. So now I built this graph, the graph which I showed here. I built the same graph here. Okay. So
Mm.
after building the graph, we have these nodes. Is path exist? Is path exist with hash set?
Mm.
Okay. These are the two algorithms. So now we can see. a path between 8 and 10. So let's look at this. Is path exist? Okay. G is a graph and start node, and this is end node, and the
Okay.
return value is boolean,
Boolean.
right? So
Okay.
what we need to do is, this is a BFS. BFS means we need to take a queue,
Okay.
and as I said, first we need to initialize all the nodes with unvisited.
Okay.
We are marking all the nodes
Unvisited.
unvisited because we haven't started our algorithm yet.
Okay.
So we mark everything for each node in the graph. We marked as unvisited. Now
Okay.
let's go to the start node.
The
This is the
initial
start
node.
node given. The start node we are marking as
Visiting.
initial node. We
Hmm.
are marking as visiting because that node you are starting, right?
Yeah.
So whenever you mark it as visiting, you want to put it in the queue.
Q.
This is very simple, right? Then yeah, BFS we use with queues. So you put it in the queue,
Yes.
and you take the another node variable, and while loop. This is very simple. Like while loop, we have to loop until the queue is empty, right?
Okay.
We need to process all the nodes from. So this is where you first one you dequeue, and
Okay.
if the dequeue element is not equal to null, if this
Hmm.
is a proper element, now we will take all the adjacent nodes,
Okay. Adjacent
right?
nodes.
If the adjacent node is unvisited, exactly. If the adjacent node is unvisited node, and that adjacent node V is the end node that we are looking for. This is end node,
Okay. Yeah.
correct?
So we'll return true.
So if the adjacent node, return true. Simple. We are not tracking any path here, right? This is simplest one. I don't want to show you the complicated one because the next one is the complicated algorithm. The next week
Okay.
probably like give me print the path, some of that. So that will take a little bit of trick. You need to store all the paths. You need to store what are all the nodes you are visiting in order to reach the destination. So this is just simply you visited or not, you found end node or not. If the node if the adjacent node of the node you took from the queue is the end node, you simply return true. If not, what we need to do, we need to set as visiting. Similarly, like just like this, for the start node you set as visiting and you put it in the queue.
Hmm.
Now we will do the same thing. That particular node as visiting, we are going to visit. Basically, we are going to visit, and we'll put it in the queue.
Okay.
Okay. So now the for loop continues. Basically, this will
For each
happen for all the nodes
adjacent
of
nodes.
a particular node you did
Yeah.
for each node. Exactly. Basically, then if you complete this process, right? If you complete this process, that means you process the particular node which you
Node.
dequeued from
So
the
it
queue,
is
you
visited.
processed it. You took the node from the queue, you very yeah, what is that?
So the node state is visited, changed into
Yeah.
visited.
So you took the node from the exactly. That's what I'm telling to say. So basically, once you complete the once you took the node from the queue, and you verified it, and so basically, and you complete the checking of all the nodes, all the adjacent nodes, and then you mark it as visited.
Okay. Okay.
Okay. I think
So,
I I
so
think I I
Suresh,
think I found a bug. Yeah, no problem.
Suresh, yeah,
Yeah,
in the line
yeah,
129,
yeah.
what if the node state is
120.
visited already?
Yeah, if it is visited, it won't be added to the queue, right? You will simply go to the next element. So
Okay. So,
this example, right? You're at the 10. Okay,
mm,
10 is the node. 10 is example. So 10 is the node you just dequeued.
mm,
Okay,
mm,
so now we are looping all
mm,
the adjacent nodes of the 10. What are the
mm,
all adjacent nodes of the 10? Let's say this is 1, this is 2, this is 3. and 8,
Hmm.
right?
Yes.
So when you get 1, it is unvisited. So we will add, it is not the one you want. So we will add to the queue. If you get this node, let's say this is 2. We'll get the 2. 2 is also unvisited. We'll add to the queue. And the next one is 3. 3 is also unvisited. We'll add to the queue. But 8, when you come to the 8, that is already, that will be, by the time you get the 8, it will be visited state. Because you started from 8. The algorithm started from 8, right?
Yes.
So definitely it will be in the visited state.
Okay.
Definitely
So,
it will be in the visited state. That means you no need to visit 8 again. We
hmm.
don't need to visit. That's why we don't add to the queue. Basically, it will just go to the next. Do we have any other adjacent nodes? It will go
Okay.
to the next adjacent node, and it will, yeah. Basically, let's say this for loop started with 8. So for loop
Okay.
started with 8. 8 is already visited. Let's ignore that. Let's add the next one. 1, 2, 3. These 1, 2, 3 will be added next time. So basically, we are ignoring if any of the adjacent node already visited, we are ignoring. We don't want to add to the queue.
Okay.
Make sense?
Yeah.
Yeah. So once you completed this process, right, then you're marking the node as visited. That's what it is. So like 8 is completed. Let's say 8, you processed 8, it will be marked as visited. So
Yes.
now we'll go back, and we'll go back to the while loop here. Take the next node from the queue. Take
Okay.
the next node from the queue and process the same thing. Let's say if you end up having no elements in the queue,
Yes.
then what it means? That means you
Um,
never you
I
never reached
visited.
end.
Uh,
That means
I visited everything in the
you
graph.
never reached end. You have visited everything. Exactly. You visited everything means you visited all the nodes that you can navigate from the start, but you will never be able to reach end. That means there is no path. So you can simply return false,
Okay.
right? So it's
Yes.
a little complicated, but we need to understand step by step. So let's say, as I said before, right? If you take the path from 8 to 6, so there is no path from 8 to 6 with this, right? So if you take from 8 to 6, you process 8, you process 9, you process 10, and you process all these nodes, but you never be able to reach 6. So you simply, by the time you process all these things, right? What will
Yes.
happen? Queue will be empty
Okay.
because you will add the elements into the queue and you are dequeuing every element in the queue,
Hmm.
correct?
Yes.
So finally, you process 8, you process 9, you process 10, and you also, let's say 1, 2, 3. These are 1, 2, 3. You processed 1, there is no nodes from 1, this is 2, there is no nodes from 2, you visited, and 3, there is no nodes, it's also visited. So every node from 8, 9, 10, 1, 2, 3, all the nodes will be status is changed to visited. Status will be changed to visited, and there are no more nodes in the queue. This is queue. There are no more nodes in the queue. That means you can safely say that there is no path from 8 to 6. So return false.
Okay.
Look at the number of lines of algorithm. Number of lines is very simple, but the complication comes into picture when we need to internalize. Basically, how can we attack? How to do the how, what are the conditions we have to add, and
It's
that is where the complexity comes,
yeah. So
right?
okay.
It's almost like it's just like our BFS algorithm. Only thing, the difference between BFS is if it is BFS, this is a BFS. We are using queue. Only thing is we are stopping when the queue is empty.
Okay.
But in case of graph BFS, what we do, we'll take the next element from the graph. We will,
We'll
in the normal traversal, we don't stop, right? We don't
yeah.
in the normal BFS, we have to visit every node. So you'll take another node from graph, and you will visit that one also. But here we don't want to display the traversal. We don't want to process all the nodes. We will process only the nodes that you can visit from the start node.
Mhm. Okay.
Clear?
Yes, yes, yes.
Yeah. So basically, yeah, tree BFS graph. Yeah, I think connected nodes is BFS. I don't know whether I'm confusing. I'm clearing because the if you see one by one, like if you see all the algorithms side by side, then we should be able to figure out the differences. Okay, what is it? See, seems like I already visited. I already seen the same algorithm. What is the difference? So BFS we already discussed a few weeks ago. The only
Yes,
difference is we don't check for any end node. BFS, that's traversal. So the last time discussed about is traversal. That's where we found how many connected nodes are all, right? So
yes.
this is the BFS traversal. See? So basically we are processing a particular path and we'll come back and go back to the next one. So it is exactly the same way, right? We took the queue and we processed the queue, and so we will do the same thing. If this is the node is not in HT, it's a basically hash table. So and we process the next one. So here is the for loop. We are processing every node from the graph,
Mm-hmm.
right? But here
Yes.
we are not using the graph. We are not using graph variable. We using G? Of course, we are using only to initialize with unvisited. After that, we are not traversing every node in the graph. We are only traversing from the start node, right?
Yes.
So this is the algorithm. When you are able to use the enumeration. Let's say you don't have access to the node, you cannot add the enum. So you already, like, let's say the nodes are coming from another API or another software. So you cannot, that particular node object does not have the state.
Mm.
The only thing is use hash table. This is exactly the what we did before. So in addition to the queue, you need to maintain hash table because something is need to be maintained to avoid the loops. We don't want to loop every infinite loop. Otherwise, what will happen is it will go back to the same adjacent node. It will try to add to the queue, delete to the queue, add to the queue, delete into the queue, right? So it
Mm.
will happen like 8 to 9, 10, and again 10 to 8, 9, 10, 8, 9, 10. It will go unlimited. It will go to the queue and remove from the queue and again add to the queue, right? So
Okay.
8 will be added, 9 will be added, 10 will be added. Again from 10, what is the visited? Again, 8 will be
Eight,
added
one,
again.
two, three. Yeah.
That's the problem. So how can we avoid that? The only way is use the hash set.
Okay. Mm.
We don't want to add the elements which we already visited before. So
Okay.
that's exactly the same thing here. So you took the hash set and added the starting node. So
No.
here we are not using the state. We are not using visited, visiting, because let's assume that that's not available. We got the node object from somewhere.
Mm.
You don't have a facility to update the node object.
Yeah.
Okay, so
Yes.
this here we are not using the status, we are not using the state enumeration, we are just putting in the hash table, and we'll take the queue. It's exactly same algorithm. You put the
So,
starting into the queue, and
yeah.
while queue is empty, dequeue the element. Yeah,
Once we visited the
yeah,
node,
ask any,
we
yeah,
are
any questions? Yeah.
once we visited the node, we are dequeuing. We are taking the node out of the hash set,
Mm-hmm.
right? No.
No, we should not. Because the
Okay.
hash table, in the hash table we will maintain all the nodes that we are visiting.
Okay.
See, you started, we need to start with start, right? So before you adding into the queue, we will
Okay.
add to the hash set.
Yes.
Okay, let's take an example here, maybe to clear easy. So Okay. Uh, Let me clear 5, 6, 7, 8. Okay, let's clear and start. So we have 5 and we have 6, we have 7 and 8, right? And
So
we
what is
have
the size of the hash
is that
set?
9 here? Yeah.
Suresh? How will we come up with the
What
size
is
of
the
the
size of the
hash
hash?
set? Or how will we come up with that
So
question? The memory
hash
aspect.
hash set does hash set doesn't require any size, right? It will dynamically
Oh,
increase,
yeah, it will dynamically increase, but um,
right? Hash
yeah,
set.
memory efficiency, time, and
So hash.
it will take the whole
Oh, you are talking about the
yeah,
the
space safe.
complexity.
Yeah,
Complexity. Yeah, complexity, space complexity. The complexity of this algorithm is order of v plus e time. That takes order of v space. Basically, how many nodes we are taking. So we are only putting the nodes which you can navigate, right? So
okay.
we are not putting all the nodes into the queue. So
So,
if you start from 8 to 10, right? If you want to find a path between 8 and 10, you will only store what are all the nodes you navigate
8 to
from
10.
8,
Hmm.
right? So
Yes.
order of v is, yeah, order of v is basically number of nodes you visited, and
Okay.
e is number of edges. Basically, from
Okay.
every from every node you will go to the different. You will visit all the nodes, right? So
Okay.
edges. It depends on number of edges.
Okay.
So it's order of v plus e. That is the algorithm. So that's a
Okay.
space. That is a complexity of this algorithm.
Okay.
Yeah. So order of v is space, and time is order of v plus e. So if you want to go here 1, 2, 3, 4, 5, you need at least 5 size of we are storing 5 elements, and at the same time complexity you need to visit every node. So that's why order of v plus e. So it's kind of every node, every edge is also counted as a time.
Mm.
Okay.
Mm.
So
Okay.
now let's walk through the algorithm with the hash set and queue. So here is a hash set. Okay, let's say this is a hash set, and here is the queue. Okay, this is queue and this is hash set. So we want to find, is there any path between 8 and 6,
Mm.
right? So we'll start with 8. So according to the algorithm, what are we doing here? Here is the algorithm.
We'll
So first we will put the value in the hash set.
hash. Yeah.
Hash set. So that means 8 will be added. 8 will be added into the hash set.
Hash it. And then
Now,
we'll enqueue it.
immediately we are adding the 8 into the queue.
Yeah.
Exactly, we'll enqueue. So we'll enqueue 8 here. Now, what are we doing? We will start the while loop. Okay, We'll dequeue the element. What is the value of n? If you dequeue element,
The 8 is the value of
n
n.
equal to,
8.
exactly, we will dequeue. Basically, this will be emptied from this queue, right? So 8,
Yes.
we got 8. Now we will start a loop. All the adjacent nodes of the 8. For all the adjacent nodes of the 8. How many adjacent nodes of the 8?
9. Only one.
All the next only one, which is 9. So for 9, what are we doing? Is 9 already in the hash set?
No. It's okay. It is
No,
not.
right?
Yeah. No.
It's not there because it's not visited yet. It's not visited. It's not visited. So we will simply immediately check, is the end node what you are looking. We are looking for 6, not 9. So this is end node, right? 6 is end
Yeah.
node. We are checking whether 9 is the one you are looking.
No.
No, 9 is not the one we are looking. So we'll go to the hash set, put the value in the hash set, and
Okay.
also we are putting the value in the queue.
Okay.
Just like exactly the way we process 8.
Okay.
The way we process 8 is we put it in the hash set. Similarly, we'll put the 9 in the hash set, and we'll put the 9 in the queue.
Yeah. Okay.
right?
Yeah.
So now what happens? Again, it will go to the top of the while loop, and we will dequeue the 9. We'll dequeue the 9. So n becomes 9. What are the
So
adjacent nodes of the 9?
9 is
Is
10.
10.
So
10 is the adjacent node, right?
yeah, 10 is the
So
adjacent
10
node.
is not, yeah. What will
10
happen now?
is 10 is not in the hash
And
set.
10 is not, exactly, 10 is not in the hash set. So now we need to
10 is
check 10
not
is the one you are
in
looking.
10 is not the one
10
we are
is not
looking
the one
for.
we are looking, right? We are looking for 6.
6. So
Yeah, and we will
we will
enter
add
into
the
the 6.
10 to the
Let's assume
hash.
that 10 is what we are looking. Yeah, 10,
Okay.
yeah, let's assume that, yeah, 10 to the hash, and 10 will be inserted into the queue.
Q.
Yeah.
Okay.
Now 10 will be, again, next step is 10 will be dequeued.
Dequeued and
Okay, 10 will be dequeued, n becomes 10, n becomes 10, and let's assume there is a path. Let's assume that this is like this. Then
okay.
what happens? Now
We'll
if you
visit
if you if you take adjacent nodes of 10,
which is 6.
now you will get 6, right? Because yeah, we'll get 6, and C is 6 in the hash table, hash set.
No. So we'll process it.
No, and next E is 6, what you are looking.
Yes, it is the end you're looking for.
This is what we see. Adjacent node. This is the unknown what you're looking. That means there
Yes.
is a simply written true. There is a path. So if it is
Okay.
like this, 8 9 8 9 10 6, there is a path.
Okay. Okay.
Yeah.
Yeah.
So this algorithm may not give you the shortest path. I need to find an example. It's tough to find an example because sometimes what happens is it will give you the longest path. It won't give you the shortest path, as we discussed before, right? So how to get the shortest path is we need to use the next algorithm. Maybe we can discuss next week. So the shortest path is like you will count how many nodes you're visiting before you going there, right? So I showed you other example. So
Oh, yeah.
you understood these two algorithms, right?
Yeah, yeah. It's clear, Suresh.
Yeah, this first one is, yeah, first one is using the state, and second one is using the hash set.
Managed.
So we can run this before discussing the other thing. We'll run this. So let's say we will have paths from 8 to 10 true and
Hmm.
7 to 6 false. We will get that. So without debugging, so all requires a little bit practice only. So in the interviews, you may not be, it's not required to write 100% compiling code, as long as you're able to understand, if you as long as you're able to convey the logic, right?
Okay.
That is more than enough. So how you're able to write the queue, and how the BFS works, and how you are checking, all these things matters. Yeah. Okay, console output, see. So we got the result, right? So is there any, so does path exist from n8 to n10? Yes. And from n7 to 6, false, right? Let's say
Yes.
these are all directed graphs. So from
Yes.
7 you cannot go to 5. So since false. Yeah. So you will get the exact same result even if I use the other one. So let's say true false, you will get true false. I'm using the second algorithm with hash set. Okay. You get the same result. So in the first algorithm, we are using the visited, unvisited state. So if it is unvisited, means simply you can think of as it's not in the hash table, hash set,
Hmm.
right? And
Yes.
converting into visiting means basically you are putting in the hash set. See, true and false, exact same results. Yeah. Okay. So okay, let me go back to this one. The first results. So the next algorithm, as I said, this one, right? So the different paths.
Mm-hmm.
So let's say find the shortest path or print the path A to F. So what is
A2,
the path to A to F? A, G, F is
AG and
one thing. A, C,
ACD
D, F
and
is another one.
ACDF.
Another one. Let's
Huh.
say ACDF is also there. So
Yeah.
now, if I ask you to okay, print the path. You need to print this path A, G, F. How can we do that? Or print the shortest path. I don't want to print A, C, D, F. I want to print A, G, F. How can we print it? So that is the algorithm that we will discuss probably next time, next week.
Okay.
Okay, display the
Okay.
shortest path. Basically the algorithm is display the shortest path. Basically the same input, same start node, same end node, but the return value is not true false. It is a little complicated. Basically it's a similar algorithm. So but it is, you need to print the path, right?
Mm-hmm.
So that's where return value is, there is no return value. If there is a path, print it. If there is no path, don't need no need to print anything.
Okay.
Okay, shall we discuss that next time?
Yeah, sure. We shall discuss it next.
Probably yeah, probably next week. Yeah.
Mhm.
So is it clear or is it
Yeah, yeah,
helpful?
it's
Basically I
really clear.
explained that kind of two ways
Actually,
to do this.
uh, knowing
Yeah.
how to construct a graph
Yeah.
and those traversal will make all other things
Mm,
easier, right? To understand and to code.
exactly, very easy. Yeah, that's very important.
Uh,
Exactly. First, like we need to understand the differences. One is like the graphs has, there could be a possibility of cycles, and
mm-hmm.
there could be a possibility of, weights. So,
Okay.
and sometimes you have, there will be no way. If it is directed graphs, sometimes you will end up in a dead end. Basically, you cannot go from there. Those are the differences from the trees and graphs, right?
Yes.
So we need to have all those in mind, like what kind of graph it is. Is it a directed graph, undirected graph? Is it weighted graph? Is it unweighted graph? Do we have circles? Not have circles? It's better to ask all those questions in the interview. If anybody asks about it, okay. So before you're writing, code, you can ask. Then they will ask you, hey, what is weighted graph? Do you know about weighted graph? What is weight? Then you can explain. That will give you good points because you already studied all the graph concepts. So that will give you additional, positive, feedback. Basically, okay, you already practiced different types of graphs,
Hmm.
right? So that's the advantage. If you start discussing more and more in the in the interview, it will make more sense. Rather than, don't jump into the logic. Don't try to solve the problem immediately. That's what I would like to say. Okay,
Okay. Yeah.
basically ask more questions and understand, and make sure you understood the problem completely, and explain the way you're going to solve. So
Okay.
as I explained here, right, whiteboarding is important. You say, hey, I will take a hash set. If you explain the things clearly, right, then
Hmm.
I will have a confidence. Okay, you already know the algorithm. You will be able to write it, even though you write some mistakes or something. I know you can. If I give you another 1 hour, you should be able to figure out. So that kind of positiveness will come up,
Okay.
right?
Yeah.
Cool, then. Yeah,
Yeah. Thank you,
that's
Suresh.
it
It
for
was a great
today's
class.
class. I hope it will be awesome. Awesome. Okay, then. Yeah. So nice
Okay.
talking to you, and then we can meet next week.
Yeah. Sure.
We'll go to the next algorithms. Okay.
Yeah.
Awesome.
Yeah.
Cool, then. Yeah. Take care. Have a nice week ahead.
Can you please share the
Okay, I'm going to
links?
stop the sharing.
Yeah. Links. 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 Today.
Yeah.